In this video, we're going to learn how to convert a mixed fraction decimal number binary in a single precision floating point representation. So in a single floating point or a single precision floating point representation, there are 32 bits. And these 32 bits are divided into three, where the first one represents the sign of the number that you're converting, and it takes just one bit. And then the next column represents the exponent, and it requires 8 bits. And then the next one represents what we call the mantissa, which requires 23 bits. So if you add the three, 1 plus 8 plus 23, it is 32 for a single precision floating point representation. So let us find the values that we're going to use to fill this table. So the first thing that we're going to do is to convert the whole number part, that is 25. So that is the first step that we're going to take, convert the whole number part. So the first step is convert the whole number part. The whole number part. And the whole number part in this case is 25. Let us convert 25 into binary. So we convert that by dividing it by 2 and noting the remainders. So 25 divided by 2 is equal to 12.5. So long as there's a remainder, there's a decimal remainder, then we say there's a remainder 1. Then the next one is 12 divided by 2, and that is 6, and there's no remainder, so we say remainder 0. And then the next part is 6 divided by 2, and that is 3, remainder is 0. And then we have 3 divided by 2, that is 1, remainder 1. Then we have 1 divided by 2, that is equal to 0, remainder 1. Then we read these values going upwards, so that we have 1, 1, 0, 0, 1, base 2. So that is the whole number portion of the decimal number that we have. And then the next step is to convert the decimal part or the fraction part. Convert the fraction part. And the fraction part in our case, as you can see, is 0.0625. That is the part that we now convert. So let's just note that is 0.0625. So a small number like this you convert to binary by multiplying by the base. So you have 0.0625 times 2. That will be 0.125, and the remainder is 0. So you note the remainder as the numbers that come before the decimal point. Like in this case, the remainder is 0. The next one is 0.125 times 2. That will be 0.25. Again, the remainder is 0. The next is 0.25 times 2. That is 0.5. Again, the remainder is 0. Then now we have 0.5 times 2. That is 1.0. Now the remainder is 1. Then you read these values downward so that you have 0.0001 base 2. So now we have converted the two portions into binary. So the next thing is to combine the two. combine the two portions that you have obtained. That is the third step. Combine the two portions or two parts that you have converted. So remember the first one was 1, 1, 0, 0, 1, base 2, and then the second one was 0, 0, was 0.0001. So you bring it here so that you have 0, 0, 0, 1, base 2. So when you have combined the two, now the next step is to move the decimal point while noting the number of steps. So because this number was a big number, 25 point something, we move the decimal point towards the left. The next step is to move the decimal point to the left. And as you do that, you note the number of steps that you take to completely move the decimal point out. So let us do that. So let us move the decimal point to the left. So it will take 1, 2, 3, 4, 5. So it will take 5 steps to make the observation that it takes how many steps? It takes 5 steps. So now this number of steps is what gives us the exponent. So it therefore means that the exponent is 5. But we have to write this in binary numbers. So what we're going to do, we're just going to convert it to binary. So we have 5, we divide by 2, that will be 2, remainder 1. Then 2 divided by 2 is 1, remainder 0. And then 1 divided by 2 is 0, remainder 1. And then you read that upwards. And as you can see, that is 1, 0, 1. So that is what we have for the exponent. So our exponent is 1, 0, 1. But from our table, you remember the exponent requires 8 bits. So for us to achieve this, we are going to top up 101 by insignificant zeros. That is zeros to the left. So remember again, let us first of all just write these in our table. We have 101 for the exponent. So we can as well go ahead and fill that portion of our single precision table. So remember, the number that we were converting was a positive number. So for positive numbers, we denote that with the sign bit of 0. So here is 0, and we have obtained the exponent to be 101. 101. But this category or this column requires 8 bits. So we want to top up these to 8 with insignificant zeros. So we have 1, 2, 3, so 4, 5, 6, 7, and 8. So now we have 8 bits for the exponent. Now let us see how we are going to fill the column for the mantissa. Remember mantissa, there's a number that you obtain when you move the decimal point completely out. So when you move the decimal point completely out, you now have 1, 1, 0, 0, 1, 0, 0, 0, 1. So this is the mantissa, the number that you obtain after you have moved the decimal point completely out of the number. So let us write this in our table, in our floating point representation table. So here, the number you've obtained after moving the decimal point completely out was 1, 1, 0, 0, 1, 0, 0, 0, 1. But this column requires you to have 23 bits. But we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we top it up with significant zeros this time, the zeros to the right. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and 23. And there we have our single precision floating point representation. So it is single precision because if you add all of these bits, they they total up to 32. Thank you for watching. Kindly remember to subscribe.